We're beginning our exploration of stoichiometry. We need to review molar mass, and then we're going to add the concept of mole ratios. Follow along as I go through your first assignment. We need to look up the molar mass on the periodic table by taking each atom in the compound and adding its mass together for a total. The first one was done for you. Sulfuric acid, which has a formula of H2SO4, is the sum of 2 hydrogens, 1 sulfur, and 4 oxygens. Molar mass is always expressed to 2 decimal places. The total for sulfuric acid works out to be 98.09 grams. We're writing these as conversion factors, so we'll write it as the mass in grams over 1 mole for that substance. We'll be using these later. The next example is calcium carbonate. So we'll need to write that name in the first box, then add up the mass of a calcium, a carbon, and 3 oxygens to get the molar conversion. Normally, we would write this including the formula for calcium carbonate, but since we're writing on iPads with fingers and styluses, it is difficult. So I will accept the mass in grams per 1 mole. Obviously, we're talking about calcium carbonate because that's the box that we're working with. So there's one little shortcut just for today, because when we do the actual stoichiometry, it will be important that you keep up with the units. From a balanced chemical formula, we can state the number of moles of each substance within that equation using those coefficients. The absence of a coefficient implies 1 mole. The first one is done for you. The balanced chemical formula of 4Na plus O2, meaning 1 O2, will yield 2 Na2Os. Those coefficients are the number of moles. 4 moles of sodium reacts with 1 mole of oxygen to yield 2 moles of sodium oxide. All right, let's do the next one. We need to balance the equation of the reaction between iron and oxygen. Because the product here, Fe2O3, seems to have the most complications, we'll start there in our balancing. We have 3 oxygens in our products and only 2 oxygens in our reactants. That's that 3-2 disagreement that we talked about when balancing equations. So put a 3 in front of the diatomic oxygen and a 2 in front of the product of iron 3 oxide, and that'll give us 6 oxygens on both sides of the equations. By doing so, we change the total number of iron in our product to be 2 times 2 for a total of 4 iron. So we'll go back to our reactants and indicate 4 iron. Now that we have the balanced chemical equation, we can state the number of moles. There are 4 moles of iron 3. There are 3 moles of diatomic oxygen. And there are 2 moles of iron 3 oxide. And that's all you need to do in that section. So you complete the rest of these in section E. Now we want to use these mole ratios between different substances throughout the equation as conversion factors. Once the equation is balanced, we can compare the moles of substances to each other. You'll notice in the example, all of the mole ratios are expressed. For this exercise, you'll only need to choose 3. First, let's balance this equation. Well, looky there, it's already balanced. That implies that there's 1 mole of boron, 1 mole of fluorine, or fluoride, and 1 mole of boron fluoride. Okay, so for mole ratios, we're just going to state that we can compare the moles of boron to the moles of fluoride, or we can relate the moles of boron to the moles of product, the BF2. And then you can pick anything else. Let's see, we could relate 1 mole of fluoride back to the 1 mole of boron, or to 1 mole of the product, BF2. There are obviously many possibilities. You just need to practice writing at least 3 of those. These sorts of conversion factors, along with the molar mass conversion factors, are the steps we will be taking to do stoichiometry. This is where we take all the warm-up exercises and synthesize them into the actual kind of stoichiometry problems that we'll be doing. First, we have to take the chemical process described and translate it into a balanced chemical formula. This begins by writing balanced formulas and then balancing the equation. So carbon disulfide is CS2. Oxygen gas, it's diatomic O2, yields carbon dioxide, we know that that's CO2, and then sulfur dioxide is SO2. But we still need to balance the overall equation, checking to make sure we have the same number of atoms on the left as we have on the right. Check your work. Is this what you got? We have 1 carbon atom on both sides, 2 sulfur atoms on both sides, and if you'll check, there's oxygen in 2 places on the right. There are 2 oxygen in the carbon dioxide and a total of 4 oxygen in the 2 moles of sulfur dioxide. That's a total of 6. Oh, looks like I made a mistake. Let's fix that. We need a total of 6 oxygens on the left, not 12. There we go. 3 diatomic oxygen is a total of 6. Now it's balanced. The question is, with 4 moles of CS2, that'll be our starting quantity, calculate the amount in moles of sulfur dioxide. So we're going to be comparing CS2. Perfect. Alarm bells in the middle of this. Okay. But as I was saying, we're going to compare it to our number of moles of sulfur dioxide. These are a lot like the dimensional analysis conversions we've done before. Start with the given information. 4 mole of CS2. The next step is to compare moles of CS2, that was the given amount, to moles of sulfur dioxide, that's the requested amount. Where are we going to get those numbers? From the balanced chemical equation. There are 1 moles of CS2. There are 2 moles of SO2. When we do the math, you multiply across the top, divide across the bottom. Notice that the units will cancel here. Mole CS2 cancels mole CS2. Our final answer will be stated in moles of sulfur dioxide, because that's what's remaining here. And the math is going to be 4 times 2 divided by 1 for a total of 8. So there's our answer, 8 moles of SO2. Now for this last question, the formula is already given, but we still have to balance it. So we need to make sure we have the same number of carbons on both sides of the equation, same number of hydrogens on both sides of the equation, and then finally, we need to check, and don't forget, there's oxygen in 2 places when we go to balance oxygen. Do oxygen last. I have 5 carbons on the left, so I put 5 carbons on the right. There are 12 hydrogen on the left, so if I multiply my water molecule on the right times 6, that gives me a total of 12 hydrogen. And then I just need to add up all of my oxygen. I have 5 times 2, that's 10, plus 6 times 1, that's 6. 10 plus 6 is 16. So I need a total of 16 oxygen here. If I put in 8, 8 times 2 is 16, my formula is balanced. The question says, how many moles of CO2, that's the question, are produced from 7.0 moles of pentane? Pentane was the hydrocarbon given as a reactant in this combustion equation. And we're going to convert from moles of pentane to moles of carbon dioxide. Let's set that up. I need to know from the balanced chemical formula the ratio of moles of carbon dioxide to moles of pentane. So I'm looking for the coefficients. There is 1 mole of pentane. There are 5 mole of carbon dioxide. Can you see how this process just would not work if we didn't have a balanced equation? The moles of pentane will cancel. We're left with moles of CO2, and all that's left to be done is the math. Finish all of this and submit it, please. Thank you.